Hi, everyone. I guess we'll get started. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ram Vadim with Atlanta Functional Programming. Last week, we kind of covered and finished up the main material of Chapter 6 related to essentially software tools and search algorithms, and it culminated into us re-implementing GPS as search. And we also started going through some of the exercises to which I'm going to be continuing today. The main focus of today's discussion is going to be a couple of those exercises. So it's going to be pretty open-ended. For folks who are joining us on YouTube live stream, feel free to post your questions in the public chat that's available to you. Jitsi folks, obviously there is a chat inside Jitsi for you to also post your questions to as well as we go along. It's going to be more of an open-ended discussion today more than me presenting more material, mainly because of the fact that there are a couple of things related to like hash table implementation of graph search and A-star search that I thought would be useful for us to go through and look at the differences between what was provided to us by Peter Norvig in his repository versus how we might end up implementing the same stuff. Additionally, there's a couple of things related to inefficiency in this chapter and exercise that I thought would be pretty useful for us to go through and at least discuss. So, without further ado, let's get started. So the first thing that I wanted to kind of go through is the tree search algorithm using an explicit use rather than recursion. This one obviously might be pretty simple for folks who are used to um, writing recursive algorithms iteratively. It's always a review, but in Common Lisp there are some different ways of actually going through and implementing this. So I thought we would go through that first. Um, so I'm gonna give kind of I'm going to first show you the previous tree search algorithm that was implemented in the repository for starters. This is kind of inside uh, the auxiliary functions. No, no, I believe it's in GPS search. Hold on, let me see. Tree search is in here? No, it's in what was it? It was in try this auxiliary functions one. No, I'm looking at the wrong thing here. This is in 1 minute. Go to our repository and grab tree search. Right. This is an actually search.lisp. I was looking in the wrong thing here. Search.lisp. There we go. That's what I wanted. Okay. That's not what I wanted. Repo. Go up here. Search. Okay. So if we look at the original tree search algorithm that was provided to us, this looks pretty straightforward in terms of what it actually does respectively recursively. We start with a set of states, the goal predicate itself, the successors, and that's it. You can think of the successors like your frontier, the number of states that you actually are going to uh, reach out and particularly search after looking at the current state if the current state does not satisfy the goal predicate. And then combining is a way of combining the results and combining the successors from the previous states that you have not yet searched through with the rest of the states that need to be searched through. So it will combine them into a single thing that you can then call again to run the search algorithm again. Naturally, anybody who can look at this and see that this cond form is a recursive algorithm where the first two cases are your base cases and the second one's recursively. How might we actually go and implement this in iteratively is an obvious question. So the way we could do this is at least one way is we use the return statement that is provided to us with loop, and we could just wrap what we currently have in um, in a loop in a loop function. So let's go ahead and do that. I'm going to go and split this, and let's see what the difference is from an assembly perspective, because this would be pretty useful to check out. Uh, so let me pull up my scratch buffer here. Um, Obviously here for some cases we may want to um, have search available for us. So I'm just going to go ahead and get some of those auxiliary functions that are in here out of the way so we don't have to redefine them. I'm going to go ahead and then run. Let me just go and grab actually using Doom. Let me go and grab yank, paste this guy. Okay, so now we have our definition that we're redefining here, and now we are good. Okay, so the difference, I'm going to go ahead and actually grab, I should have actually grabbed, let me do this actually instead. Let me grab the original one because we're not going to do that many changes to this. Okay, and here what we'll do is first we're going to just simply wrap this guy in a loop. Okay, now this is going to obviously then call the same states multiple times, um, and we need to naturally in the tree search function call, we're going to have to actually get rid of that recursive call to handle the states that we are dealing with. Okay, and that's a simple thing that we can end up doing. So the way you would do this is first here in this case, in the base cases, we just simply need to return. We need to wrap this, and we need to return fail. Okay, and this will actually go ahead and return the same stuff that we have. Give me just 1 second here. I'm gonna because I copied this, everything, the indentation is all messed up. Here in the next one, we know that if we end up grabbing if we satisfy one of the states, if any of them are the goal states, what we could do is then just run, we just need to return the first of the states, okay? Same thing as before, nothing major here. Um, it's the recursive call that's going to end up being slightly different, which is here, instead of calling out the tree search, what we're going to do is we're going to modify states to have essentially the frontier get updated, and this update function is then ultimately going to then be used by um, the uh, uh, what's it the call to the goal state when we actually leverage it. Okay. Now, since only the combiner is required here, that means then this all goes away. and we end up coming up with this kind of function structure. So this is one way of implementing this. Just to show you that this actually works the way we expect it to, let's let's run this other example that we had with a star. I think is the one that we ended up using. Not this, not this, not this. Let me see if I can actually pull up. Um, Let me see if I can pull up the call to a star that we had earlier. Because a star ends up leveraging tree search via graph search, actually. Um, let's do, you know what, this might be an easier one. Let's do this one instead. Tree search on the is6 using the next two section here. So the first thing that we do is let's do this. Um, we need to first turn on debug search. Okay, so now search is turned on. Now we do tree search. We start with 1. Our goal is 6. Is For those of you who are just joining us and haven't actually been following along in the book, is 6 is a predicate generator. It'll actually generate a lambda for us to do this to generate the next two states given the first current state. Next two also is our actual successor function, and our combiner function is there's a built-in prepend that ends up create using the just like cons to actually go and cons the heads to the beginning of the list, so to make things easier. And you can see that we run search on the next two and we ended up getting 6. That's actually incorrect. That does not that does not seem right. I mean, at some point we do run it, but it doesn't actually. Oh, right, right, right. It's because I need to put this here in this call. Let me see if I could do this. Okay, there we go. And you can see that this gets generated the way we kind of expected it to. Um, Notice though, whereas and also, just to show you that this actually works in graph search too, because graph search here, as we define it, if I remember correctly, this was also implemented in using the same thing. We can actually do the same sort of stuff with graph search too as well. We could switch this up to actually become iterative. But let's first look at the disassembly of this tree search call. Um, okay. And let's see if we can actually improve this, because there is another way of doing this using essentially an accumulator to maintain the recursive call, but then just change it so that we actually accumulate the results. But I don't know exactly the right way to actually set that up. But basically, instead of using the recursive call that we do, we grab the combiner states, and then what we do is we attach the next set of states into it in the call, and we literally accumulate the search results as we are actually checking to make sure that the goal has been satisfied. Instead, here what we're doing is we're grabbing the search states, that is the states that we have to search into, and then we actually go in and uh, run the predicate on each of those search states. So let's see how this works. Now, one thing to keep in mind is and for our own sake, let me go ahead and define this again here so I could look at the disassembly in both cases. Okay, and let me see if I could also split the window. No, that's splitting the wrong window. I want to split this window. Nope, it does not allow me to do that. Okay. Um, all right, let's see if I can do this. I did. Okay, so first things first, you will notice that compared to the 1 second, this does not look right. One moment, I may have redefined the wrong thing. Search, here we go. Okay, here we go. So in our recursive version that was defined, an immediate thing will become apparent. The size of the actual disassembly, the way it's getting reconstructed, is much larger in the recursive case than in the iterative case. Okay, um, this is a few bytes different, so it isn't that much of a big deal, but it is something to be aware of that the generator of the actual code is going to be slightly different. The structure is going to be slightly different. Additionally, um, this call to debug here that I created that inside the iterative case I put it explicitly in the default case when we're actually grabbing more stuff in the from the frontier. Um, Notice that the structure of it is going to be exactly the same for debugging, but before that we're actually doing less than what we would be normally doing inside of the recursive case, in that it's no longer setting up a bigger stack frame to actually go and run the recursive call. Um, some of these symbols and some of these instructions will may look small, but they do incur an expense. The main ones is for the recursive call, because you are incurring a stack frame every time. The memory actually ends up growing, just as a natural result of maintaining all those recursive calls as you're running through the search. Um, with Lisp and this ability to actually look at the functions, you could then tweak up how you may end up leveraging certain data structures in Lisp, uh, and it will have a direct effect on the actual generated assembly that's being done, at least with respect to SBCL. I wanted to kind of show that out and call that out for folks who are interested and have a vested interest in doing high performance. Um, um, okay, all right, all right. Let's go on to the next thing. Um, Another way of actually going through this is using do. I believe you can actually still do list, but even with do list, it becomes a little bit more messier. Um, and you can actually do not do list. Sorry, with the do form, we could implement essentially what we done here in using do, but it the I think you don't get that much of a performance boost, but uh, and so if folks are interested in actually looking at how we might doing it with do, let me know. Um, I want to call out some of these specifics here with the loop example, just mainly because this one is something that I was studying earlier today from this the solution that Norvik presented. I was like, huh, this looks pretty. I would not have guessed that this would end up generating a very more efficient assembly. So there are more improvements to this that I believe that can be done to make this even more faster, a faster iterative solution. But for now, I thought I'd at least bring up this one just because it had some interesting characteristics that we can discuss. Um, Let us go to, let's see here. So for the next question that I wanted to cover, I want to go back and look at this sorter that we were using. Okay. Um, and talk about some of the inefficiencies that are dealt with this sorter. At least as it pertains to uh, not just running the sort necessarily, but just how it constructs the argument to pass into sort. Okay. Many of you know, I hope many of you know that append, what it does is a non-destructive append, where it takes the first argument, makes a copy, and then uh, appends the second argument to that copy before returning it. So to give an example, if you have a just a quick review here, um, let's say you have this, you have an A that is basically 1, 2, and you have a B that contains 3, 4. Append A and B will give us 1, 2, 3, 4, but A is still intact and B is still intact. Okay. This tends to be pretty, it could become pretty expensive depending upon how many times you call it and how large the list can get. Um, and then the other aspect of this that's particularly part, which is it takes that copy and then runs sort on the entire result of the sort of the data structure, rather than doing like an insertion sort when dealing with already sorted old states that are available as part of the first argument. So this in alone will cause some inefficiencies when you end up leveraging this just as is, although the code is much cleaner. Um, so one way to actually work around this is there are a couple of functions available to you in Common Lisp that can allow you to um, effectively write the same thing without having to use a pen. The first thing that I forgot about when until I saw this um, going through this book is this merge. Um, So merge is a function that literally does, as the name indicates, an merge between two sequences, destructively though, into the particular result type. And this is particularly important because destructive operations tend to be more efficient over time. You have to be careful about the destruction. This is why um, the there is this myth that Common Lisp and most Lisps, other than, and there is an exception to this, which is Scheme, are pure functional languages, and they aren't. There are some cases where impurity is required, but if you hide it behind a functional interface, which is what Common Lisp does very successfully, you will end up having something that can be used functionally 90% of the time, and places where destruction is required and you need to do something a little bit more efficient in place, you have that option with you rather than having to deal with what Haskell does, which is it goes and um, requires you to create like a monadic transformer to actually make sure that the modifications and the in-place arguments are done behind the scenes. And that can work in some cases, that can work, it can't work in other cases. I wanted to at least pull that up for those of you who are looking at this and say, well, you could do this enclosure in a functional way, and I just want to point out that if you have set F and there's a way to do it destructively, um, if you hide it behind a functional interface, the rest of the users aren't none the wiser, and you could do some things a little efficiently. There are some cases where it's useful to have that kind of functionality, and we see that more and more. So using this merge function, we're going to actually, I'm going to take the example that I had earlier, just to kind of show you what this would do. Star B, okay, and the predicate that we're going to use is let's do greater than, okay, and it merges both, and if we look at A and B, you could see that B got modified because we took greater than instead of less than. Okay, so let's see how you might leverage this to actually go and implement a more efficient version of the cost function that we currently have. I also would like to maybe quickly look at the assembly of this just to see how might this change when we implement this more efficiently. Okay. I scrolled too fast. Let me do this. Okay. So we move the stack pointer back into our AX. We grab the effective address here into RAX. So the first stuff is kind of setting up the layout for the cost function to grab the actual cost function itself. Um, then where is then from the jump that you see there, we are essentially going to construct a new lambda that is returned by this function that ends up building up the additional layout on how to call out to sort. So we need to create like a fun call in order to actually really see what happens if we end up calling out to this function, because this is all function construction. This isn't the actual function itself. Um, but just to give you an idea on how might that look if we ended up doing say disassemble of, okay, let's do a quick append of call A and B, because this is the main thing that we ended up having to, oops, that's right, because this gets evaluated. We have to make this into a lambda that just runs pence. Okay, and this is the more important piece here. You could see what this call ultimately would do is something equivalent to the following, where we load the data into the particular registers here, and then you'll see this all the time. function pointer gets stored into EAX for the effective address, and then we end up running a jump to essentially call that function pointer. So these three instructions here are pretty typical that you would end up doing. You load the arguments into the appropriate registers, and then you end up calling this. Now, by the way, this approach is pretty common regardless of which instruction set architecture you have, although they may do things slightly differently in terms of how they will set up the stack frame or prepare to actually run the function call. But the idea is fundamentally the same. In the case of some architectures, like if you're using, like, say, MIPS, um, you have additional registers that will you can use to uh, store the return value before you get out. The way to actually do it here is you put it back into the stack frame, and you jump to the effective next instruction, which will take that information out of the stack, the stack that it actually was returned to, and then it'll be able to continue on execution. Um, so this is kind of what it currently does. Let's see how it changes if we end up implementing it. Um, so let's run sorter. The same. It's going to end up being the same interface. Okay. We're not going to change anything here. But now what we're going to do is we're going to merge as a list destructively. Okay. And we're going to default to using greater than instead of less than in this particular case, um, because the cost function that we ended up using, uh, when it's less than, it will end up being what's it? It effectively is going to be the same that you would end up doing with whereas with what you did before. But and I'll show you an example of this. Just give me just 1 second here. So the first thing we have to do is we're going to also return a lambda that takes the new and the old. Then we're going to merge as a list the following. The first thing we're going to do is we're going to first sort new using greater than with the cost function. Okay, so we're going to keep all the most expensive cost functions at the beginning. Okay, so we're doing it in descending order. All right. Then we're going to combine that with sort old, sorry, greater than same cost function. Okay. And what this will return us is the sum from the most expensive to the least expensive um, in terms of cost. So let's go ahead and say we're returning uh, more, more efficient cost function, more efficient combiner that sorts according to cost function. Okay, let's see how this works. 3 arguments, but wants 4. Ooh, did I miss a couple of things? Yes, I did. Okay, so I messed this up here. So instead of sorting it, we don't need to actually sort it because this should already be sorted. Get that rid of, and good. All right. Let us try this guy. So let's make our cost all 1 for the time being. Okay. 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 So let's create a sorter with the cost function being just a lambda x declare ignore x1. Okay. Oops, did I mess that up? Yeah, I did. I messed that up. This is, oops, go back. Okay. This is the wrong thing. Do one. Better. There we go. So now let us see if we call this on fun call sorter on list 1 2 list 3 4. What happens? Sorters unbound. Oh wait, dummy. I messed up here. This here. No. Run that. Oops, not that. Run this. There we go. And then run this. I should have assigned it to a variable, but since I already have a history variable, I wasn't going to. All right. So what I did was I created the Lambda factory with the more efficient thing, and I just fun called it into it. And you could see that this would be the same as if we ended up doing this here, and we ran the same creator, and we tried to fun call it, and you'll end up getting the same results. Okay. Um, and what just to even show this more interestingly, let's go ahead and do this and say this is def parameter inefficient sorter. Okay. Now let's go here. Oh, efficient is inefficient. Just because I was having some, there seems to be some stall between whenever I type into my Emacs and the when I run streams, I notice that I periodically get a stall between Emacs and the buffer. So apologies for the misspelling there. So let's do this one, and let's run the same sorter here. And now this guy is going to be def parameter. Here we go. Efficient sorter. Okay. So now let's do fun call inefficient sorter on list 1 list 2 4. See what happens. Interesting. The cost does not do it, just does a merge. Let's see what happens if we do this one. This is going to be based on this one. This is going to be based on, that's right, this makes sense. So this also shows you that it's not actually sorting the results, it's sorting it based on the actual cost function that's being created. Okay. All right. So what's the next one that I was going to go through? It was going to be ah, this is the more interesting one. that we're going to be probably spending some time on, which is writing versions of graph search in A star using hash tables rather than lists. Uh, so let's start with graph search itself, and then we'll move to A star um, because graph search is nothing more than a visiting function that you can actually write pretty quickly. But also because a lot of the stuff that we use for graph search, I think if I remember correctly, A star was implemented using graph search, and we can leverage that to our advantage as well. Um, yeah, this is based on a very similar thing that we can end up leveraging using the same approach as graph search. So let's go back to graph search. Okay, now graph search, if you recall, took states, our goal predicate, again, successors and combiner. So the same as tree search, but it gives you two additional things. One is an optional state equality function and the old states that you've previously visited. Um, so this is something that we need to change to using we will change to using a hash table to see if we have visited before. So I'm gonna first grab let me grab the whole function here that we're going to deal with because we don't need to change much here. We're just going to be checking to make sure that we the way we do visit it, we check to see if we what's it the visited states aren't part of the frontier is one way of actually handling this. Um, or in this case, what we're going to do is we can use the um, internally we can actually call in the fun call, the kind of combiner, the actual check to see if a filter function to actually go and filter out those states that we've actually visited before actually calling this guy. Um, so we don't need to necessarily change too much. The one thing is whereas this here, this states that we actually are combining, that states holds the set of states. We're going to have an intermediate one that'll actually gets called into this with the new states and the old states. So let's go ahead and first grab the uh, the new states with that information and then go from there. Um, this one here is right, because this is the name of our new states. Okay, and our combiner takes in, if I remember correctly for this, we can go and look at how the combiner is being constructed. Check to see. Right, because we're using add join to do the state lookup right now. So our old state is now, okay, hold on one second. Let me just double check something here. This one here is here. Just need to look at one thing, which is right. So in here, new states is the function call that actually generates the new states that we haven't actually been seen before. And internally, that actually already handles the state equality by using the member function, which does a linear search on each of the collection, the list that was passed in, based on the equality that you have to determine whether or not something is a member of that list. And this obviously is inefficient. So what we need to do is in the states that we ended up passing in, if we ended up leveraging a hash table, we can actually go in and handle what's it? A lot of the search has just by doing a quick look up to see if it's available. And that's just computing the hash and then checking to see if the hash is actually available. It's a constant time operation, as most people are aware. So we need to go and change actually not just this necessarily, but we could certainly change the what's it the new states to actually go in and update. Yeah, we need to go and change this to actually the new states to actually go and grab the set of states that we haven't seen before. So let's go ahead and grab this guy here. Boom. Shift. Okay. So our successors also is going to change too as well, because successors has to compute now um, states in the form of hash table too, in that it needs to be able to actually uh, provide us, given the current state that we're in, the next two states, but being states in the member of the hash table of states that we're actually looking at. So this is going to be pretty interesting. So we have essentially, before we're returning a state, our computation actually leverages, like we don't want to necessarily um, change the generator of the successor states. Those we'd want to keep the same. So next two should should be computed and returned as a list, but then we can actually go and load them into the hash table. So let's see, how might we do this? Um, well, to begin with, let's fix this one thing. Test equality here is going to be based on hash table equals, which if I remember, uh, we have get hash to actually go and grab the key, and the key is going to be get hash hash, and then I don't believe we have a testing functionality anymore, because with get hash, you're just computing the hash table. We're not going to change the hash function. Um, make hash table. Let me just double check that make hash table doesn't give me. Oh, okay. So what we do is when we generate the hash table in the beginning, before we start anything else at the call in graph search, we need to pass in. Got it. Okay, I'm starting to see how we might approach this with the. So the goal is to not to change the interface of graph search. The interface of graph search should use these same arguments, and we're just simply internally changing the implementation. So what we'll do is, give me a second. I'm just making a let form here. So there we go. And let's. Oh wait, why did I do that? Okay. Okay. So now states hash is going to be, I'm going to call it states ht, which is the hash table representation of the um ooh, yeah, this is also going to be a problem, isn't it? Because the fact that um the recursive call to this also takes in the rest of the states, which means we want to use the same hash. Ideally, we want to use the same hash table for for new states as well as old states. So I can't just simply do that. We're going to have to change this function a little bit. Um, let's do this. This is going to be our hash table thing, and um, old states hash table. I think is probably what we want to do. And then let's see. Oh, right. Hold on one second. Let me do some undoing here because we don't want to necessarily change that. Okay, I'm gonna do this in two folds. Let's fix this. Let's finish this one thing here, and then we'll move this on to the next one. So basically, what we need to do is a couple of things. One, when we construct the hash table, we need to make sure that the hash function. I mean, the hash function is going to say we're going to check to see if the equality test is the test that we would end up using. So here we would end up passing in as our test the state equals to construct a hash table. All right. And then that would handle what we're currently doing as the member. So when I just call now get hash will end up using the state equality to actually go in and make sure that it's available there. Same thing here with the old states. We can just do get hash state on old states, and then this will also handle this one. So now we grabbed this to being um, this simple predicate. So if it's not a member of the current set of states or a member of the uh, old states that we previously visited, then we are okay. Now, um, to test whether it has been seen before. So the question is use a hash table rather than list to test whether a state has been seen before. So we've now actually technically updated new states to handle this, but um, this alone I don't think fixes the issue because we need to Ooh. We need to return originally the there's a way for new states to take in the hash tables and keep them with it. Then that would be ideal because then um just give me a minute here. I'm just trying to think what would be the easiest way to do this. We could change. Because states hash table requires us to, yeah, we're going to have to somehow pass in to new states the hash table that we've encountered first. Okay, so let me see if I can do it this way. Okay, we will do not tree search. Where are you? Graph search. There you are. I'm going back to this additional idea, but it's a small modification. CPR F. States HT. Let's make the hash table here. Hash table. Okay. With the same hash function that we have, the only difference is our test is going to be state equals. And additionally, we're going to also have the old states HT, which is also going to be a hash table with test state equals. And then and we're just going to use booleans. So this is going to be just bit flags. The key is going to be the hash. The value is going to be just nothing more than whether it exists or not. So it's kind of what we're currently going for. Let's see here now. And what we'll do is we will add the additional states into. So instead of add joining the state with the old states, we will just insert the state into the old state's hash table. I think that would take care of that piece. Um, so that passed in, yeah, since that's passed in, we have to actually uh they're keeping track of it just for the sake of passing it into the um we could do also a map hash, but I really don't want to actually construct a list every time to make the function call. and that's a recursive function call too as well. Well, it's a iterative well, it's a recursive function call. Graph search actually does a recursive function call. Um, so folks who are following along, the issues is we have so we can easily make the hash table insert the hashes into the hash table to keep track of old states and new states that have not been seen before. Okay, that's actually fairly straightforward exercise. The challenge then becomes is if you want without is it possible to actually um, change the implementation without changing the interface in such a way that we could only use the hash tables to represent the frontier here. There is a couple things that I could do to actually minimize that, but that, ooh, no, that's still not a problem. We can't use flat. Doesn't really freaking matter there to always construct the old states because it's going to add computation because you're reconstructing the data structure every time you make the recursive function call. So ideally, what we'd want to do is, at least the way I'm currently thinking is we want to change graph search to actually take in a hash table instead. But that changes the interface, and that's not what the question is asking. The question is asking is writing a version of graph search that uses hash tables to test. So it's only for a test. So I guess we could do that. We could we can make a hash table inside of the test here specifically takes each of the list of the old states and the new states, computes the successors, and then just removes based on what we've added into the old states and the new states hash table that we've just created in new states, uh, those that aren't actually doing it. And since it's going to be small enough, it's going to be fine. I think that's okay. Let me do it that way. It'll be the recreation is going to be pretty stupid, but it's going to be not. It's going to be fine. So the first things that we need to do is let's call this instead of states. Let's call it states hash. Okay, and we're going to have to construct the hash tables first. So let's go do this. Okay, states hash table, make hash table. Well, it's going to be test equals. This is also going to be hash table state test equals. And then what we do is um, this is we're going to have to populate do list um, state in states set f get hash key is going to be state in the new states hash table, and we're just going to return a 1. We're just going to set it as a 1 or a 0. All right. Um, and we're going to do the same thing for old states. Actually, why the hell did I do that? We can just name this state an old state. Okay, and we have this old states. So now this should work. Okay. Let's see if this does what we expect it to. Hopefully. So I just simply changed new state. Everything else is the same, except this is going to be pretty inefficient in terms of the fact that I'm not changing the interfaces so that we pass in the hash table all the time. So we're recomputing the hash table every time to get the updated set of stuff, but this should be okay since we already have the list. So let's go ahead and call this guy. Okay. And let's run the example that is in the book. Okay, what was the one in the book? That one was, I think, graph search 1 or 2, or something like that. Or is 6. Yeah, is 6, same thing. Okay, so let's try this with that. Okay, so let's pull up the tree search call. Just change it to graph search. There we go. Change this to graph search, and this should just work. And we see that it's pretty fast. So I'd like to see the difference in the disassembly now between new states that we just created with the use of the hash table or the old states. Now we are incurring some memory because of the fact that we've introduced another data structure and we're keeping it, we're recomputing it every time. But I'm curious as to how this might look like versus the other one. Okay. New states. This one takes in. Okay, so this is all function layout here. This is calling the symbols. Here we go. This is the more important piece. So we're grabbing the lambda states in the construction of the function pointer, and then we storing it in this. So I'm curious how this is the main thing that needs to look like. The function called to remove a if is irrelevant for this piece of the puzzle that we're actually going to look at. Unfortunately, okay, so let's do this. Run that. Let's do this here. Okay, this is not working the way I expected to. Let me just see if I could just grab. Invalid argument trap, invalid argument trap. Oh, I need to provide, okay, in order for this to actually work the way it's expected. So this invalid argument trap is because of unbound symbols. So give me just 1 second here. I need to do this thing, make a let. It's okay to do this sometimes, just to fake the code into thinking what it's supposed to do. And let's see this. Warning. Oh, give me a second. I also have to do that too. State equals. Okay, there we go. Now we're getting what we expected. Almost there. There's a couple of unbound stuff that's still missing. States. 1 second. Okay. Yeah, it's still having an issue with the callable issue. Let me do this. Go back to this. Is to make it so that lambda state. Let's do this. Declare ignore state 1, always returning true, just so that I can actually generate it. And I'm still getting the invalid trap there. Okay, there's another way of handling this. We create a simple function. There's always multiple ways of skinning a cat to do what you kind of want to do here in Common Lisp. So I'm just defining a function with that interface that I want, just so that I can actually look at the specific disassembly of that function construction. States, old states, and state equal, right? Yeah, okay, good. Okay, disassemble test. Okay. Damn it, this is still giving me the function layout. It's not actually giving me the function call. All right, I've given up. I was trying to show you guys the differences between how the function is actually going to be interacting, because basically with new state there are some optimizations that can be taken behind the scenes to generate more efficient lookups, but that's happening underneath at the assembly level than at the level of the actual function call itself. Now, one thing to note and one thing to point out is my approach here is a bit more expensive than what there are probably more efficient ways of doing this. One is naturally somehow keeping track of the hash table for subsequent calls and always add to it, not actually construct it every time. Um, but given how small some of the stuff that we're doing, and more importantly, our actual data structures that we're leveraging is actually being computed in real time. We're actually leveraging functions to generate the next two functions. This sort of recomputation, it will, in this particular case, will turn out to be pretty inexpensive. So you can get really far with what we have there. Um, are there questions? Okay, let's see let's start looking at A star now. A star is probably going to end up being the same approach because I believe the new states is going to be using. Okay, yeah, this is going to be old paths is what we really need. Okay, with old paths, we're gonna have to do something slightly more different. Um, it's going to be the same idea that we had before. The slight difference is here is with old A star, you might have to actually try the in the insert paths especially, um, you need to uh, actually let me see if insert paths actually gives us, where is that insert paths? Okay. Insert path is already kind of doing a destructive operation. So what we have to do is here we need to um, construct a list, a hash table, take all the paths in there, and then uh, filter out the list of paths that was so we could do the same thing. Let's do this very quickly. Y for Y. I don't want to change anything in here. Go into my scratch buffer. And then we just do this here. CPWR. Do let path ht being make hash table. Let's see if we can actually leverage this with an empty default, because I don't want to add any more stuff into this. And then what we'll do is we'll say that unless um, get hash path ht, what we'll do is we'll set f get hash path ht with saying visited, and then what we'll do is grab the merge, because that means we can actually return this. And in the case that it's not true, oh, Never mind. I'm going to have to say, um, no, that's fine. We could do it that way. We could still, um, no. We actually have to do something else, not unless. We have to do, yeah, you have to do the following. We're going to have an if statement here. If get hash path, just return paths because we're not going to actually insert it into it. Otherwise, what we'll do is we'll do a prog n here, prog n, and we do the following. Okay. So what we're doing is if it's already in the paths table, once we've constructed the paths table, which we haven't actually populated yet, we will just return the set of paths because it's already available for us. Otherwise, we're going to go ahead and add it into the oh wait, this is not useful here. Otherwise, we'll just go ahead and merge that path into the current path that I have with the path total cost. So let's do this one thing. Let's go through and first populate this table. Do list p in paths, setf, get hash p paths 1. All right. So we populate the path hash table. We check to see if the current path that we've just passed in is part of the path hash table, and if it isn't, if it is, we return paths saying that it's already been visited. Otherwise, we don't. So this should do, I would think, the same thing that we had earlier. So let us remind ourselves how it used to work before we check to see if it did work. Okay, so first clear REPL. Then I'm going to pull up the A star example just to make sure that, you know, okay. So here, path states A star, path states A star search. Our starting path is going to be list make path with state 1. Our goal is 6 as usual. Our successor function is next 2. Our cost function is going to be just 1, make everything equal cost. Our diff is going to be how close we are to the actual answer. So how much further we are. Everything else is going to be different. So we end up doing this search. Hold on one second. Invalid arguments 3. 1 second. I must have start this again. Oh, I forgot to pass in. Okay. Passes. Okay. Goal. Goal. Successors. Find path to invalid number of arguments. Hold on, I think I may have messed up something here. Oh, hold on 1 second. Let me try this one thing. Let me try restarting by reloading search for this beginning thing. Now, search is never used. 3. Let me do this. See what happens here. Go to A star again. There seems to be an issue with find path. Start and Oh, did we mess up something? See if that works. Find path for some reason got messed up. Okay. I don't know why that got messed up, but that should not have occurred. Okay, so we actually got our original implementation working here. So let's try updating this to using our version of insert path. So we now redefined insert path. And path 2 is not of type hash table when binding hash table. Hold on. Why is that even attempting to bind a hash table? 1 second. Get hash key hash table. Oh, oops. I knew I messed up something. Okay. Now we will get it right. Boom. Okay, so I want to do a side-by-side comparison of the execution. So let me run this one more time with insert path being defined here. This way, and just make sure that and that. Let's run this first. Let's redefine it here. Run it again. And you see that you get the same results. The only difference is now we're now leveraging a hash table. And again, before this past hash table is getting computed ever again, so there is some inefficiencies in this computation recreation, but the benefit of it is you've now, at the very least, your interface has not changed. So you can actually leverage this dictionary up front, but just temporarily, and you could keep track of all of the additional stuff. And since it's small, again, I go back to the fact that we are dealing with a small frontier here. This is a pretty quick computation, so you don't have to necessarily worry about not being able to do that uh, and leveraging it. So that's about it for today with our 9 minutes left. So, and that all I really wanted to kind of discuss. Next week, we're going to be talking about um, Chapter 7, and Chapter 7 is about on symbolic computation, which is a really fun thing to do. So you're going to actually learn how to write a simple version of Maxima, uh, which is one of the first computer algebra systems that were out there. For folks who are following us along, and if you like and our videos, please like and subscribe to get up-to-date information as things get posted onto the Atlanta Functional Programming YouTube channel. As usual, AFP is an organization that promotes functional programming. We have online and in-person meetups in the Atlanta area. If you are a resident of the Atlanta area, we are in need of a home for our in-person meetups. We used to actually frequent a lot at the Atlanta Technical, the ATDC down in Tech Square, but unfortunately, that kind of went. We no longer are there. We're actually looking for some new home to actually host our in-person meetups. So if you are a resident of the Atlanta area and you have ideas, please reach out to me. I'm Bugram on Tech 404 Slack, as well as Functional Programming Slack. If you guys are not on the Tech 404 Slack, but are members of Functional Programming Slack. Additionally, if you are all the Lispers out there, I am a member of the Lisp Discord server, so please DM me if there are particular topics that you want us to, you know, cover as part of the Common Lisp Study Group. Once again, I'm your host, Ram Vedam with Atlanta Functional Programming, and I hope to see you guys next week when we start talking about Maxima. Thank you all for joining us. Have a good Saturday.